All right, welcome back everyone. We got 4.2 audio programming. It's been a while, but we got something a little bit different here this time, all right? So we got some buzzwords here. We're gonna be looking at WAV files, things like PCM, binary mode for reading, or excuse me, just writing to files, audio wavelengths, things like RIF, FMT, and audio data, and of course file seeking, so that we can kind of seek around that file and do some things, okay? Now, let's break it down a little bit deeper, okay? The first thing we're going to break apart is what is a WAV and a PCM file, okay? There's a slash here, whoops. There's a slash here because they have a lot to do with each other, okay? We're going to take a deeper look at what audio actually is, and what I mean by that is, you know, audio as itself. What is audio? And then audio and, digital audio. What does digital audio look like? And how do we represent real audio as digital audio? We're going to look at the WAV audio encoding. Notice how this time there's an E here. And we're going to do a little bit of research there, right? So we're going to go and look at some documents that really highlight that encoding really, really well. And if you were to try and program with any other file type, this is exactly what you would need to do, okay? Then we're going to create our audio header with an example, and then we're going to kind of roll through here. We're going to create some random audio sound at first, and then we're going to go back and we're going to do a 2-channel audio, which is going to have different sound in the left channel than in the right channel, okay? Okay, so what is a WAV and a PCM file? So WAV is pronounced wave, right? W-A-V. You don't say it like that, you just say wave. And it is an audio file that stands for waveform audio file, okay? Very simple, kind of just, very simple, similar to other audio types, okay? Then we have PCM, which stands for pulse code modulation, which is a way to digitally represent audio signals. So, think of it this way. We're using an integer here to represent an audio signal in the form of a wave, okay? So PCM is the actual data here, and that's what this picture really is here. If I have a WAV audio file, there's going to be a lot of header information up top, and then it's really going to be a lot of pulse code modulation, okay? Now, that's not always true, but a lot of the times it is true, okay? Now, as always, there are external libraries that exist to easily manage audio, and, it is important to use those, but it is also good to see what lies underneath the abstraction, okay? If you want to, make recording software and you have to deal with audio a little bit, it might help to use those libraries. But if you really want to break it down, you want to do something different than's available, then that's really where you have to know what's going on behind the scenes. All right, let's take a deeper look at audio here. So audio is a wave like sine and cosine functions. In fact, that's exactly what it is, okay? You cannot just put random values for your PCM and your audio file and expect it to generate sound, okay? Because sound is oscillating, okay? It is represented like a wave, okay? Hence when you hear the word sound waves, okay? So we need to use a sine or a cosine function to generate the data, the digital data that we need to make a, wave file. Okay, now there's a couple things that you need to know about these functions, right? If you're looking at this stuff, you've probably seen trig functions before, okay? But a little bit of refresh on those key details here is one thing that we really need to look at is the distance for the period or even the frequency, okay? So if the period is longer, that's going to have a different sound than if the period is closer together, which I'm not going to kind of give away how that will change the sound just yet. And if you think about if they were higher, for instance, a lot of these are being raised to the same height, but this one only reaches about an amplitude of 1. So amplitude is also considered our height. And this blue one here has an amplitude of 2. It reaches a height of 2. That's going to create a different sound, okay? So keep that in mind when we go through this. This is really the bread and butter. We can use a lot of this function here. We're going to kind of use that function. We're going to change it just a little bit to kind of get our values in a better place. But that's basically what we're going to be using. Okay. All right. Let's get into some research here and kind of see what these things look like. All right. So if you were going to do any, oh, look at that. We're already ready for it. If we were going to do any encoding or any writing of a file that you had never seen before, this would be the first step, is researching how that file is supposed to be designed, how the header information is going to be so that any computer can properly read it. So we're going to Google WAV file encoding. You can see we got some results here. And obviously I have been to this website before, but this is what I have found to be a really good one. Now it's kind of hard to see. Let's zoom in here a little bit. Okay. But this right here represents, this top here, represents the header part, okay? Now, in our picture programming, our header was very small. We had, 4 pieces of information that it was a P3, encoding type, our width and our height, and, the amount of colors we could have, and then it was just data. For a WAV audio file, we have much more stuff going on, as you can see here. Okay, we have a chunk ID, a chunk size, format, subchunk 1 ID, subchunk 1 size, audio format, number of channels, sample rate, byte rate, block align, bits per sample, subchunk 2 ID, subchunk 2 size, and then our actual audio data. Okay, and that's because, quite frankly, there's a lot going on with audio compared to a simple, PPM image. Okay, and we're going to break this down. You're going to see that all we really have to do is write a few things that are very short, and then we can get into our data. Now note this on the right here, the size of the bytes, okay? So a byte is 8 bits, right? And one character is generally represented as a single byte, or 8 bits, okay? So you can think of this as this would be 4 characters long if this was written as a string, which it is, okay? Chunk size, that could be an integer. That would be, we would need to maybe do some special stuff there. Okay. And I'm going to break that down and, how on earth are we going to make sure that something is written as 4 bytes or something is written as 2 if they're both, maybe possibly integers. Okay. So I'm going to get to that. Now, if you scroll down a little bit further, you can see a lot more information on what things mean. So for instance, what I said it's not too bad is look at this. Your chunk ID just contains the letter RIF in ASCII form, which because we're going to put our file in binary mode, that's actually going to be really easy to do. We're just going to put RIF and then look, boom, chunk ID done. Look at this, chunk size 36 plus subchunk 2 size, which would be down, here. Okay, so that's just a simple addition, right? Format contains the letter WAV, not too bad. Okay, now I'm actually going to break into these things a little bit more when we code them. But there's a few more things. Look at this. Contains the letters FMT with a space. Our subchunk 1 size is 16 for PCM. That means 16 bits. So all of our data that we use for PCM needs to be represented with at most 16 bits. Okay. Now, if you think about that, an integer is 32 bits because an integer is 4 bytes. So whatever number we use can only have 4 bytes. So we're setting a max value here when we use a 16. Okay. Audio format, we're saying we want PCM, so we're going to put a 1. There could be other values for other types of compressions. Number of channels. So number of channels, this one's actually really easy. Mono, which if we put a 1 there, means that the same exact audio is going to play out of both ears. Okay, so if you wear AirPods or headsets, you have 2 of them, a left ear and a right ear, the same exact audio will play in both. Stereo means you're going to control those audios, those channels, the left and the right, differently, which is more of what happens. Okay. Now, the sample rate is how many pieces of data to represent 1 second's worth of audio. Okay. We're going to be using 44,100. So we're going to have 44,100 pieces of data for our sample rate every second. Okay. Now, the rest of this is just, this one's reiteration here, the bits per sample, but the byte rate, it's just calculations. You take the sample rate that you had, which was 44,100, you times it by the number of channels that you're using, which you get to pick 1 or 2, and then you multiply that by bits per sample divided by 8. You're dividing by 8 again because there are 8 bits in a byte, and it has to do with byte rate. Okay? And then bits per sample, I believe, bits per sample, we did already. Well, we'll put right here, which is just going to be 16 bits because we're choosing 16 for PCM. We could have obviously chosen different ones, but because we're using PCM, we're going to use 16 bits. Okay, so that's really just 16 divided by 8. So it's just 2 for our situation. Block align, the number of channels times, again, the bits per sample divided by 8. Okay, now there's extra stuff for different file types we're not using. And then down here, look, we're just going to put the word data. We're going to do the subchunk 2 size, which is the number of samples times the number of channels times the bits per sample divided by 8. And then finally, you've made it, you're going to put your actual sound. Okay. Now, because we have to put this in binary mode, this is an example of what the top of the header file would look like. Now, you can see they've broken it down here really, really well. Okay. Like really, really well, they've broken it down. And, you know, it's still going to be confusing though. All right. Like I know it's broken down really well here because like we got, you know, squiggly lines telling us what's what. But if you think about it, you know, when you had a picture, you may have wanted to open that picture in its raw data format and seen like, hey, what was the width and height? Did it actually make it over there? And it's going to be a little bit harder to see that when it's in binary mode. Okay. But we'll still be able to get this pretty good. Okay. Now there's a ton of other stuff about this. All right. You know, audio files can get very intense. We're going to keep it pretty easy. Now, if you feel overwhelmed by all this different stuff here, you know, we're going to go through, we're going to code all of this once. The part that I care about in this lesson is you changing the actual data for the audio. Okay. Not necessarily all of this above. This above here is just kind of plug and chug, set it up. And then the data is where I care about the manipulation. So I'll really be doing this upward part here. Okay. All right, let's get back to our slides. And I think we're actually going to jump right into doing some coding right now. So it looks like I had programmed all of that in also here. And it's a little bit more simple when you look at it here because there's not so much other information going on. But these are a lot of the values that we will be using. Okay. Now, if you were writing your own program, maybe some of these you would want to get from the user. Maybe you'd want to tell the user the sample rate. But in our situation, we're going to hard code it, kind of keep all those other things to a minimum so we can focus on the audio. Okay. Now, the one hard thing about what we have to do here, it's really the chunk sizes. It's hard to tell what the size of something would be until we've written it, right? So subchunk 2 size is supposed to tell us how much data there actually is. Well, we take the number of samples, right? The number of channels. Well, we don't exactly know how many samples there are yet, because that's our data down here. We know what our sample rate should be. We know that we should have 44,100, samples per second, but what if something ends halfway through that second, right? So we're gonna do some file seeking there so we can just actually, every time we run it, see exactly how many pieces of data we wrote. And then we're gonna go back to our file, seek to these locations and update them, okay? All right, let's do a live code. Let's get into this. All right, so here we are, we have a file. We have the IO stream that we're including and the F stream. And we have on the right here our actual, header format so that we can easily reference this, okay? And most of this right here, we're just going to go ahead and hard code this as global constants, okay? So let's focus on those first 3, which is called the riff chunk. So let's do this, go riff chunk. And let's create a constant string. And again, the field name is called chunk ID. So I'm going to call it chunk ID. Do we have to call it that? Not necessarily, but it's going to be really helpful to refer back to the standard if we make any errors. Okay, so constant string chunk ID equals RIFF. Okay. Now, other things might be able to go there, but that's what's going there for the type that we're using with the PCM. Okay. Now the next one is the chunk size, right? Which we saw is 36 plus the subchunk 2 size, but we don't know the subchunk 2 size right now, and it's not even defined. So we're just going to create a string. We're going to call it chunk size, and we're just going to set it equal to 1, 2, 3, 4 dashes. And the reason why we're setting it equal to 4 dashes, because in the standard it says we need 4 bytes. And here, each character represents a single byte. So we're going to use 4 bytes to kind of take that up so we can easily replace it with the 4 correct bytes later. Okay. Now, the next one is format, and we're going to set it equal to WAV, just like the standard says. Okay, so that's the riff chunk done as far as creating the variables, hasn't been written to the file yet. Okay, now the next one is the FMT chunk, subchunk, right? There we go. Okay, so we're going to, again, we're just going down the list here for the header information. So constant. Now this one is also a string, and it's going to be called subchunk1 ID, and it's equal to FMT with a space after. Okay, this is because there is different information that could go here, and a lot of that different information is 4 bytes, so we need to still put a space there because it's always going to look for 4, even if the one that we want has less. So we need to put a space. Do not forget that space, or your whole, everything will shift off and it won't be able to be read properly. Okay, now we're moving all, pretty much integers for like the next 6. Okay, so we're going to go subchunk 1 size. Okay, which this one we do know the subchunk 1 size. And if we look over here, the subchunk 1 size is simply just 16 for PCM, so we're putting 16. Okay, now we also know the audio format, that is equal to 1, standing again for PCM. All right, now the next thing we're going to do is constant int the number of channels. Now we're going to do 2-channel programming. I think it's more interesting to have the right and the left speaker doing different things at different times. So we're going to go with 2, but you don't have to do 2. You can do 1. You can have the same audio come out of both, and I will talk about the adjustments that you would make for that. Okay, now from there we're going to do constant int sample rate, which for this one we're choosing 44,100 because that is a common standard that you would see. Right now my audio is actually in 48,000, so it's taking 48,000 samples per second. Obviously, if you have a higher number, you can have better sounding. Lower number, maybe not as good sounding. Of course, there are still a lot of other factors there, but you could think that the more data you have per second, the better the sound could be, but also the bigger the file size. Okay. Now after that, we have our sample rate. We just did our sample rate. We have our byte rate. Okay, now our byte rate is equal to our sample rate times the number of channels times the bits per sample. Right, now the bits per sample is really just our subchunk 1 size, so we could just put 16 divided by 2. Now I know that seems redundant. We know that value, in fact, let's just do it the right way. Let's put subchunk 1 size, because we know that's going to be 16, and that it'll be divided by 2 to be 8. But just if we decided to ever change the subchunk 1 size, then our byte rate will still work. Okay. Now after that, we have bits per block align. So constant int block align, and the block align is equal to the number of channels. So num channels times the bits per sample again, which again is really just our subchunk 1 size. Okay, and so we're just going to use that instead of the variable bits per second, because that's the next one which we would define, which we haven't even created yet. Okay, so subchunk 1 size divided by 8. Okay, hopefully I didn't do divided by 2. I did do divided by 2 in the last one, so that's an error there. Okay, this should be divided by 8 because we're dividing out the number of bits in a byte. Okay, all right, now let's see what we got going on here. All right, then we have finally the bits per sample. So constant int bits per sample, and that is equal to 16 because that's what we're using right here for PCM. Now these values could be different, but these are the ones that we're going to use. Okay, now finally we have really not too much left for the header information. Okay, we're going to have constant, and I think we're going back to string here. Yeah, we're going to do constant string subchunk 2 ID, and that's going to be equal to just the word data. That's it. That's the data subchunk. So let's put that comment. Data subchunk. Okay. And then after that, again, we're going to have another string. So constant string, and we're going to do subchunk to size. And again, that is 4 bytes of information. And so we have to use 1, 2, 3, 4 spaces because we don't know the actual data yet. Okay. Now, one of the things I kind of glossed over was the byte sizes here. If you notice, the subchunk 1 ID was 4 bytes. We see that here. But if you look at the subchunk 1 size again, well, 16, that's a number, that's an int. An int is 4 bytes. That works. But for the next one on audio format, it's also an int. That's also 4 bytes. That's going to need to be 2 based off the standard that they've set. And we can represent numbers with 2 bytes, but we just need to, we're going to write basically a special helper method to achieve that, so that whenever we want to write these ints, we're going to make sure they get saved with the right amount of bytes. Okay, so let's write that helper method right now, and this helper method is going to include some new things. Okay, and I am putting this above. So we're going to go and create a helper method called void, or return type of void. We're going to call it write as bytes. Now, the first thing this is going to take is our file. It's going to take it as an off stream, and we're passing it by reference. So we're just going to call it file. Okay. So when we call this write as bytes, right, where it takes that first thing is the file we want to write to. The next thing it's going to take is the value that we write to it, and then the byte size. Okay. And that's really the important part here, is that byte size. Let me make that a little smaller. Okay. Let me overlap this a little bit. There we go. Okay. So every single time we now want to save one of these integers, we can call this function itself to implement it, and we can just send the byte size that we want it to be saved at. So if the standard says it's 2, we'll put a 2 there. If the standard says it's 4, we could put a 4 there and ensure that it's saved as the appropriate amount of bytes. Now, the way we do that is we're using a function from offstream called write. Now, write is going to take basically a char pointer and the amount of bytes that you want to do it, that you want to save it as. Now, because integers can be chars also, we're going to do a reinterpret cast. And this is something pretty new here. Okay, so reinterpret cast. And in these angle brackets here, we're going to put constant char star. And again, that's just the casting part of the value that we sent. And then we're going to pass to that function the byte size that we just listed. So this is a lot of new stuff. This is a lot of new stuff jammed into a single line of code. So let's break this down. Okay, you're calling the file that you're sending to this function. Okay, offstream has a built-in function, because remember, it's a class called write. All right, and the whole point of write is that it allows you to kind of write things in binary mode. Okay, or to write things a little bit differently than you would by specifying the byte size. But you can't just send it anything. You have to send it a constant char pointer. Okay, and so the way this all working is you're taking the reference of the value that you sent, and then this line is going to take that value and it's going to turn it into a constant char pointer. Okay, by casting it. Now, if you remember casting, just kind of a preview here. If I said, double, let's do this. How about, okay, if I said int x equals 0, double y equals, 3.5, okay, and I want to make another double z and add x plus y, there's going to be some casting going on here, right? Because this is an int and this is a double. So you can explicitly cast it, and I can go, hey, look, I want this to be a double temporarily just for this expression, okay? And that's what we're doing here, all right? Now, it's not too important that you know how to use this for other things, but it is going to be necessary for this, okay? All right, back to it, okay? All right, so we have our helper method. We have all of our header information. let's start off by writing this header info to our file, and then let's look at our file and see what it is, okay? Kind of do our best to verify that it's going to be the right thing. And we're going to be doing this all in main to kind of keep the abstraction simple. So I'm going to create a file that I'm going to write, call it WAV, all right? And I'm going to open that WAV file. Again, we'll call it test.wav, and we'll put it in binary mode, all right? Now, again, very important here to note is that everything is just a text file. Some of them, yeah, we put in binary, but binary in a file is really also just a type of text. Everything you see on your computer goes down to text files, okay? So we're going to go if wave.is open. Oops, because we're going to check to make sure that file is open. And then we're going to start writing things to that file. Now, the good news is when we want to write a string to a binary file, it's going to work really, really well with just going like this. Right? That was our first one, chunk ID up at the top here, right? We can just write it the way we would write it to a non-binary file, okay? And so we're going to go through all these 4 strings right here, and we're just going to write those, okay? So we're going to write, we wrote the chunk ID, right? And now we need chunk size. And notice how I'm not putting any end L's, because if you remember the standard over here, they're just boom right next to each other. And these spaces here are really just put for us. There doesn't even need to be those spaces, okay? So this is just going right down the line. So chunk ID, chunk size as the standard list. And then we're going to do format. And then that is our riff chunk. And then I'm going to make a space to kind of separate those. And we're going to do our subchunk 1 ID. Okay. Now here, this is the first one we get to because we did our 4 strings that we can write normally. Here's where we get to our 4-byte integer that is okay to be 4 bytes. But again, an int on different systems might be different things. So we're still going to use our little helper function here and write it as 4 bytes. And then when we get to the 2-byte ones, like the audio format and the number of channels, it'll just help us to do it the same way. Okay. So we're going to call that function. Sorry, let me scroll up there. All right. It's called write as bytes, which you could have called it anything you want. So write as bytes. We're going to pass it the file WAV. Okay. And then we're going to send it the subchunk 1 size. And then pass the amount of bytes it should be written at. So 4. Okay. Let's write it as bytes again. We're going to go WAV this time, just like the last time. And now it's the audio format. And that is, looking at the standard on the right, 2 bytes. And we're going to do it again. Write as bytes. Pass it a WAV. And we're going to put the number of channels. And that is, by the standard, 2 bytes. Then we're going to go write as bytes again. Oh my gosh, I can't spell it right. WAV. And this time the sample rate, which is 4 bytes. Then we'll do write as bytes again. You guessed it. I should just be copy and pasting that at this point. And we're going to do the byte rate, which is 4. Write as bytes again. I should have given this a smaller name so I didn't have to type it out every time. We're going to put in the block line. And then we're going to go write as bytes again. And this time it's the bits per sample. And that is 2 bytes. Okay, so let me just verify it was supposed to be, what am I doing wrong? Oh no, that was 4. Okay, so some size is 4. So 4, 2, 2, 4, 4, 2, 2. That's perfect. Okay. Now, let's go down here and let's do our 2 for the data chunk that we know. So we have WAV subchunk 2 ID. We have WAV subchunk 2 size. All right. And then finally, we're at the fun part, the actual writing of the sound. Okay. But first, let's do a quick run here. Whoa, not what I want to do. Let's save this. Let's open this up in the terminal. Let's just view our output of our file. So I'm going to compile this. What do we got? Block line expected before constant. Interesting. What line we got here? 18. to do constant int. Oh, so the previous line I left off the semicolon. I'm sure you all caught that. So that messed everything up. Compile, and then we got to run it. Okay. All right, so nothing runs as expected. However, we should now have a, test.wav file. It's 44 bytes long. We're going to open this up. It says that it can't support unsupported binary text. Probably just don't have the extensions, but as you can see, it's compressing it here. Yeah, I'll do that one later. All right, but we have our riff. Look, we have our 4 chunks. The strings we wrote are showing. Our data is showing up as different stuff, a little bit of compressed data, and that's okay. All right, but this is going to be the hard part about your audio files, is when you see something that you don't like, or that you don't understand why is the audio sounding this way, you go to your data and it doesn't look very friendly. Okay, so you really have to be looking at your program and observing what you're doing. All right, okay. So we've successfully written the header, right? It's even, look, you can even see a sound icon there. It's knowing that it's a sound file, okay? But we now need to get into the actual data part, okay? Now for this, we need to find some additional constants, okay? And these are going to be needed for our data, So let's go up here and let's drop down and let's add, for starters, a duration. So constant int duration, set equal to 2. So it'll be 2 seconds long. That's a value you can change, okay? And we're going to go constant int, and we'll do max amplitude. Now this one I'm going to explain. If you remember, your sine is a wave, okay? So we're going to go 32,760 as our value. How did I get this value? Let's see if I got my calculator here for us. Okay. So here's the thing, right? If a integer is 4 bytes, that's 32 bits. That means that, you can do 2. Where is the better mode for this? Let's do scientific. There we go. I have to, what? Should have had this calculator prepared. Okay. All right, well, we'll just have to, oh, wow, I'm so ridiculous. Okay. So if an integer is 4 bytes, that's 32 bits. That means there's 32 zeros and ones. So that's 2 to the power of 32 as your highest value. But technically, that's not very accurate because one of those needs to represent 0. So it's more like 32 or 2 to the power of 31. Okay. But very, very close here, right? This would be the max value or close to it. Now, because we're using 16 bits, okay, and sorry, this would include positive and negative numbers too in this. So technically you need to take half of that value, and you can go to that positive and you can go to that negative. So let me re-explain that. So I just realized that was a terrible explanation. We're going to go 2 to the power of 31 because that first one also needs to store if it's a positive or a negative. And so this is really your highest number minus 1 because of the 0. Okay. Now for 16 bits, we go 2 to the power of 16, 65,536. But again, that's all of the numbers, including the negative ones. So if we could just divide this by 2, take a 2 out of it, and 32,768, you minus that 1 because it's 0. And really the largest number you could do is 32,767. I just did 32,760 just because I was approximating when I wrote this, okay? But that is the highest value that our sound can be for this because we're using a 16-bit number, okay? Because we set our chunk size, our bit size, bits per sample to be 16, okay? So I'm setting my max amplitude of my sine wave to be 32,760, all right? So sorry if that explanation wasn't very good, okay? Now the other thing we're gonna do is we're gonna set a frequency value, which is also can really be considered like a phase shift in your trig functions. It makes your function very close together. Your waves are very far apart. And I'm just gonna pick, make this a double. So, oh my goodness. And I'm just going to pick an arbitrary number of 250 Obviously, later we might want to change that to something with a decimal, but I'm just going to choose 250 now, just to, to change it up. Okay, the higher the number, the closer those waves are going to be together. Okay, so I'm going to put them very, very, very close together. All right, now let's go back down here and let's start coding our data. It's taking a little bit longer than I thought it would. It was probably a very long video. Okay, so we got for int, and I equals 0. We're going to loop through our audio, but think of it this way, okay? We need 44,100 pieces of audio per second, okay? So our for loop is going to need to do 44,100 times 2, or really, it's just going to need to go, my goodness, my fingers not on the keyboard right today, taking our sample rate times our duration, which here would be like 88,000 something, right? We're going to program it in that way so that if we decide we want to, change those values, our program will still work, okay? So this for loop is going to go about 88,000 times. Now, the first thing we're going to do is we're going to calculate an amplitude value and an amplitude for our sine function, and then we're going to calculate the value for our sine function, and then do some more manipulation to get a channel 1 and a channel 2 value because we're manipulating the speakers separately. So I'm going to go double amplitude equals double, because I'm going to convert my for loop value into a decimal, I, divided by the sample rate times max amplitude, okay? Now, what on earth did I just do here? Okay, think about this. This is going from 0 to about 88,000, okay? And I'm going to divide it by 44,000 times 32,000. What is that going to do? Ensure that my amplitude never gets bigger than this max value of 88,000. It's going to actually ensure that it always stays to be a very, very small number, and it changes very incrementally, okay? And I'm going to show you that in a second on how that works, okay? Sorry, actually this is read a little bit differently. I'm messing up my order of operations. I'm going to take I divided by the sample rate and multiply it by the max amplitude. So this will be, chunking it twice, okay? So this is going to go to 88,000 divided by 44,000. This is going to go from 0, this is going to go from 0 to basically 2, okay? And then multiply by my max amplitude, all right? Now, why did I choose it that way? You could have done that a lot of different ways, but I wanted to at least have 88,000 different values that moved slightly, okay? We could have changed our for loop up to be a double there and move from maybe 0 to 1 over 88,000 times. However you want to do that is fine. You just need to make sure that this value changes, okay? Because your amplitude is your height. And so I want my sound waves to increase in height as the sound plays. I don't want them to stay at the same height, okay? So I'm going to go double value now, which is going to be the value of the sine. I'm going to go sine function, which I need to probably call CMath. We'll see about that. See if I get an error from that. I'm going to go 2 times 3.14, right? Because that's for pi, times my input number times the frequency divided by the sample rate, okay? Now, why did I choose these values? Well, for starters, this is a pretty common formula that we have here for sine functions, right? If you use a sine function, the very first thing that you're going to do here is you're going to take 2 times pi times whatever number you're inputting into it, and then you're going to multiply it with the b value, right? Which, if you see it in your normal math class, this frequency will be represented by a b value. Now, again, we're dividing by our sample rate here because we need everything to work out to that number. We need the cycle to repeat every sample rate, okay? Because every second is going to change. Now, if you're like, this was extremely confusing to me, that's okay, all right? The basic goal of this section here, all right, because I'm trying to get a little fancy with the audio that I'm showing you guys so it looks cool. The basic goal here is that you need to, respect the max amplitude, okay, and operate as a wave, all right? So that means that you can literally do something as simple as putting a sine function in that never exceeds your max amplitude and that just oscillates on the same pattern. But if it always goes to the same height, it's always the same sound. Okay, and that's very crucial there. It's always the same sound if it goes to the same height. Well, it's very close, but it's going to be louder if you get to a bigger height. Okay, and I want my height to change so that you can see that. Okay, now we haven't actually put anything in the file, so I need to do channel 1, and I'm going to make that amplitude times value. All right, if you remember that sine function, it's a times the sine of, right? So our amplitude times whatever value we just got. All right, then I'm going to go double channel 2 equals max amplitude minus the amplitude, oh my goodness, times the value. Okay, so what is exactly happening here? All right, my first channel is getting bigger. As this value I goes up and we're multiplying with the amplitude, it's just going to get bigger. It's going to go from a low number to a high number, the height of my sine function. This one here is going to do the exact opposite. You can see I'm going to take the max amplitude and minus it by amplitude. Well, if amplitude is increasing every single time this for loop increments, then this is going to result in a smaller number each time. So I'm really going from a high number to a small number, because if my max amplitude is 32,000, I'm minusing by, let's say, 1 the first time, it's very big. But after a while, I might be minusing by 1,000, 15,000, when you get a smaller number, and then I'm going to times it by value. Okay? Now, what this means is that our left ear should be going from low to high, and our right ear should be going from high to low. Okay? Now, when you write in your different channels, that needs to be like left channel, right channel, left channel, right channel. Oops, hold on here. So I can scroll down there. Okay. Sorry, it's getting all glitchy. You can see it kind of here in this diagram. See how it has these arrows for the right channel here, and it's pointing to all these right values. And so it is left channel, right channel. So then the left channel is all the left. So you read this like this. Look, left channel, right channel, left channel, right channel, left channel, right channel. So you're just going left, right, left, right. So I have to put them in basically at the same exact time, not at different times. So I'm going to use my right as bytes function again, because they need to be, how many bits do they need to be? Data needs to be 4 bits. I know I'm not really showing it anywhere, but it's 16, no, 2 bits, right? Because we said it was 2 bytes, because it's 16 bits. Okay, I got this. So we're going to go channel 1 value and make it 2 bytes. Okay, because it needs to be 16 bits. And then I'll save the channel 2 value. Okay, now at this point, we do not actually have functioning audio. All right, we have one more thing to do. Well, actually, we get like 3 more things to do. Okay, but the end is nigh to see some actual results here. If you remember those chunk sizes that we just saved them as this, well, now we're actually putting data in. So we need to go back and actually put values for those, all right? And the way we're going to kind of do that is with file seeking and with telling where we are. So there's a function for the offstream called tellp. So I can go int start audio equals wave.tellp, and that's going to go, where am I in the file? Okay, which at this point is going to be right after this. Okay, and then it's going to I'm making a marker there. I'm saving that number to start audio. Okay, then after I write all my audio, I'm going to go int end audio equals wave.tellp again. So if I'm at the like 80,000th bit here, and I was at the 50th bit here, 80,000 minus 50th, it's going to tell me how many bits elapsed from this whole for loop right here. Okay, so that's really helpful. I'm going to have that, but I need to subtract them first. Okay, now in order to actually do that, I now need to go to where that audio was. All right, so if we look, that was actually right where we started almost. In fact, that was 4 bits earlier than where we started. 4 bytes earlier than where we started. Okay, so we're just going to do this. We're going to go wave.seekp. So tell P tells where you are, seek goes to a location in the file. And I'm going to go start audio minus 4 bytes. Okay. So if you remember when we wrote to files before, it just kept going down. Well, now with seek, we're jumping to like backwards. Like I actually want to go back and write over something. Okay. And then we're going to write as bytes. I'm going to go write as bytes, and I'm going to send the wave file, and I'm going to go end audio minus start audio, because that's how much has elapsed, and it needs to be saved as 4 bytes per standard. Okay. Now that only told us one thing. That only told us the subchunk 2 size. Okay. But we still need to do the other one. All right. Which is our chunk size, which is, 36 plus the subchunk 2 size, or it says more precisely 4 plus 8 plus the subchunk 1 plus 8 plus the subchunk 2. We're going to do it this way though. Okay. So we're going to seek again to go where that other one was. And the way we're going to do this is we're going to say we want to go to the 4th bit after the beginning. So iOS with the scope operator BEG puts us at the beginning of the file, and we're saying we want to seek 4 places after that, because look, your chunk size was 4 places after. So now we've moved location of where we're writing. I'm going to write as bytes again, and I'm going to pass it wave. I'm going to say end audio, right? Because that was the end of our audio. And I'm going to minus 8 off of that. Okay. Now I'm minusing 8 off of that because 36 plus the subchunk 2 size, if you look at this, your header size, it's about like 44 bits. So if you really just do the whole thing minus 8, you're fine. Okay, it's another way of doing it. Or you could have taken 36 plus the subchunk 2 size, totally fine. Okay, I'm going to put it as 4 bytes. I'm going to finish that line. Okay. Now we're actually almost somewhere here. All we have to do now is after that, we need to close that file. So that is a long if statement. So we now need to wave.close. Okay. All right. Let's give this a compile. We're actually almost done. Oh, I do need to include CMath. So let's give this another compile here. And everything is good. We run it. Everything is good. Let's go take a peek at our, yep, we have a ton of data now. But this doesn't look very helpful, right? Like, how do I know it's actually going on here? And before we play this, I'm going to introduce you to an open source program called Audacity. It is really good for audio, okay? If it loads up this year, okay? And it's really going to help us visualize our audio here, okay? So watch this. I'm going to take that file, which is on the desktop. There we go. And just drag it in. And you can see that this is what our audio is looking like. Now let me zoom in a little bit. All right, and look at that. There's our sine function. This is all that matters, is that you put a sine function in, you're going to get sound. But if you notice that my sine function is growing bigger on one channel and it's growing smaller on the other, like we talked about, all right? And, well, we definitely have an error here because it's not decreasing in size. But we'll make some quick adjustments on this one. I think I know what's going on there. And we get some different stuff. So this is going to mess up our audio a little bit. So before I play this masterpiece, okay, let me go back. And I'm kind of noticing here that if I take amplitude times value, I might be exceeding our max amplitude here, okay? So I'm just going to kind of, I'm just going to divide a 2 off that. And I'm going to see if that kind of brings things down here, okay, without doing too deep of a dive on there. So let me close this out. Drag that back in. And that was helpful, okay? All right, let's play this and see what it sounds like. All right. Now, because I am mixing is as mono, you probably would not have heard those come in differently. You would not have heard it come in as a stereo where it's 2 different ones, okay? But as you can clearly see, we do have 2 different channels here that are operating very differently, right, as we look along this, okay? Now, this could have been a very confusing lesson. There was a lot of new stuff in this one, and this is going to be really the bread and butter of the different things that you are going to have to do when you try and do something on your own, okay? But at minimum, you need a sign function. If you put a sign function that is the same, and it's just going up and down all the way through, then it's going to make the same sound, all right? But I am looking to see you guys do things with 2 channels or 1 channel, a combination of both, and to make some different sounds. Now that was a 2-second sound clip. You do not need to make music, but definitely see what kind of sounds you can come up with. So if you couldn't hear it, I'll just put it in on the audio. But let's see what it sounds like again. Sounds like a bell, right? But yeah, so temper your expectations on the kind of audio. We're not making beats yet, although you could try. And let's actually get back. This is pretty much wrapping this up. Let's go see what our quick code is. Wow, that was a really long video, and I am really interested to see how long this is going to be. Okay, so, and I said quick code, I mean mini lab. All right, so notice again, same thing as our last mini lab. You do not have to use class data structures. I shouldn't have said filters here. It should have been sounds. It will greatly increase, the work, but if you want to be, a super user, by all means, okay? Now, very similar guidelines here. Your program will need 5 different sounds, okay? Those 5 different sounds do not have to be in the same file. I'm not really putting a minimum time on this, although, a quarter of a second I think would be too short, all right? It would be very difficult to hear it, but, you could do it as long or short as you want those sounds to go, all right? The sounds do not need to be beautiful, but they need to be different. So examples would be adjusting different channels. So one starting high, one starting low like I did, and then changing it at the same time or at a different time. So you can start them both low and go high. You can, have a really rapidly change the sound like a siren, okay? You can adjust frequency levels for different pitch sounds. So that's actually something that I wanted to do, but I just feel like I've taken up too much time. Adjust that frequency. See what it does, because it's going to bring your sign function much closer together with a higher number. Make it lower. See if it changes the sound. Increase your amplitude. See what happens, okay? Now, each audio needs its own function. Now, the user should be able to interact with your program by entering in the name of the audio to be created. So you're going to present them a list of options, and they're going to choose the one that's going to spit out the right file. If you want to get advanced, you can ask the user to supply certain values that would change the audio. So, for instance, you could be like, hey, user, tell me the frequency that you want. Tell me, certain details. How many seconds would you like your audio to be? Stuff like that. Is that required? No. But again, you want to be a super user, you got to go the distance. Okay. So I hope you guys enjoyed this extra long video, and I will see you next time. Don't forget to like, subscribe, and comment, all that good stuff.